Okay, class, so we were looking at all of our waveforms, and we've got those. So now we're going to be looking at these interval measurements. Now, interval measurements are important in ECG interpretation. You don't always have to measure them to be able to tell what the rhythm is, but a lot of times you will miss other things that are happening to the patient if you don't look at them. And at most facilities that you will work at, if you're working with monitored patients, especially if they're a continuously monitored patient like on a telemetry floor or on a intensive care unit, it is actually a policy that every shift a strip will be run and you will measure all interval measurements. So when we're looking at our intervals, we said our P wave was atrial depolarization, and then we had that hold in the AV node. So the first interval measurement we're going to look at is the PR interval. It is from the beginning of the P wave to the beginning of the QRS. Now, I know it says PR, so you think, okay, I have to go all the way here to where the QRS goes up, but it's actually where the QRS starts. So from the beginning of the P to the beginning of the QRS, that is our PR interval, and that is telling you how much time it is taking for that impulse to get from the atria, from that SA node, travel through the atrial pathways, depolarize the atria, and then how long the AV node is holding it for. So that measurement should normally be 0.12 to 0.20. The next interval measurement we look at is the QRS interval. So remember, our QRS tells us ventricular depolarization, and depolarization is the impulse traveling through the ventricles, causing that chemical and electrical process to happen so it can spread that impulse through the ventricles. The QRS measurement from the beginning of the Q to the end of the S. Now again, it doesn't matter if you have a QR waveform or an RS waveform, whatever that waveform is, we call it the QRS measurement. From the beginning of it to the end of it, it's telling us how long it's taking the ventricles to depolarize, to get that impulse. And then again, like I mentioned, contraction is going to happen immediately afterwards. Now, the ST segment is not a segment that you measure unless it's elevated or depressed. Then you would measure how much elevation you have or how much depression you have. But you always want to look at that ST segment from where that J point, where it notches and changes directions. And that ST segment should be flat. It should be isoelectric on this flat line of the waveforms. And then our T wave is also by itself not a measurement we look at, but the other measurement we measure is from the beginning of the QRS to the end of the T wave, and that's called the QT interval. And the QT interval tells you how long it's taking the ventricles to depolarize and repolarize so it can do it all over again. Now, the one waveform I didn't talk about when we looked at the waveforms in our last video was the U wave. The U wave is it's very rarely there. In probably 100 monitored patients, you might see it in one. And they're not really sure the significance. It's a waveform that comes after the T, and it is not as big as the P wave, so it definitely looks like just this small, tiny little blip. And sometimes it has been linked to electrolyte imbalances. For most people, they can't even find a significance to it, and most people do not have it, but every once in a while you'll see that U wave. So our PR interval from the beginning of the P wave to the end of our or to the beginning of our QRS complex, there is on ECG paper, and ECG paper is standardized. Each big box of ECG paper is 0.2 seconds of time, 0.2 or 0.20, however you want to look at it. Within each box of the ECG paper, there's tiny baby boxes, and each of these little baby boxes is 0.04 seconds of time. So there's 5 of them, 0.04 times 5, that's how we're getting our 0.20 for the big one. If we're looking at ST elevation, then we look at these boxes. If we're going this way for voltage, then it's 1 millimeter of voltage. But when we're going this way, we're measuring time. So when I'm measuring my PR interval, I start from the beginning of the P wave to the beginning of our QRS, and I count how many little boxes I have. So it's 1, 2, 3, 4, 4.5. So 4.5 boxes. Each little box is 0.04 seconds of time. again, that would be 0.18. So a normal PR interval is 0.12, which is 3 boxes, the 3 baby boxes, to 0.2 or 0.20, which is 5 boxes. That is a normal measurement. And again, it's telling us how long it's taking the atria to depolarize and how long the AV node is holding it for. So in this example here, again, you see the big boxes here, and inside each big box is 5 little baby boxes. So from the beginning of the P wave to the beginning of my QRS complex, I count how many little boxes I have. 1, 2, 3, 4, looks like 5 here, 5 small boxes, times 0.04, this one would be 0.02. When I'm looking at, why are we not moving here? Okay, on this example here, now again, in this first example up here, you're looking at your P wave is going upright, your QRS is primarily going upright, your T wave is primarily going upright. So you are probably in lead 2. In this one here, my P wave is going up, my QRS is predominantly going down. A little bit of it's going up. My T wave's kind of flattened out here. So this one here is a good chance I might be in an MCL. But for right now, let's just look at this PR interval, beginning of the P wave where it starts to go up to the beginning of the QRS. It looks like I'm about 3 small boxes here. And again, 3 boxes. Each box is 0.04 seconds of time. That would be 0.12. And then, oops, so sorry. This thing is super sensitive for some reason. Does not want to go back. Okay, well, it already moved me over to my QRS, so I missed that other one. So when I measure my QRS interval, my QRS is whether I have a Q, an R, and an S, or a QS, or a RS, whatever I do, that's called my QRS interval. So this one here, it's measuring my Q wave. It goes up for my R, and then it comes back down. I don't really have an S for this one, but you can tell where it notches or changes directions. Now, a normal QRS interval is it is 0.08 to 0.11. It should be less than 0.12. So 0.08, or I'm sorry, 0.06 to 0.11 should be less than 0.12 for adults. And so if I look at this one here, I have 1, 2, 2.5 small boxes. And again, each box is 0.04 seconds. Excuse me, 0.04 seconds of time. So that would be 0.10. So that is a normal measurement. This example here, for my QRS, it goes up for the R, comes down for the S. You can see where it notches or changes directions. It looks like I'm just a hair over 2 boxes. They called it 2 boxes. So 2 boxes at 0.04 seconds per box. Again, that would be 0.08. And then this last example here, I have a Q. It comes up from my R, and then again, it just notches and changes directions here. I don't really have an S wave. So again, I would still call it the QRS. And so from where it leaves the isoelectric line to where my R wave goes on over, it looks like I'm 3 boxes here. 3 boxes at 0.04 would be 0.12. So this one is actually too big, and we'll talk about what that means next week. So the QT interval, we said, is from the beginning of the QRS to the end of the T wave. So it's telling us, remember the QRS is telling us ventricular depolarization. And so this is telling me ventricular depolarization and repolarization, how long it's taking it to get the message, contract, and get back to rest so it can do it again. The QT interval should be 0.40 or less in normal heart rate ranges. So when we look at bradycardias, when we look at slow heart rates, sometimes the QT interval can lengthen a little bit. But for normal heart rates, it should be 0.40 or less. It is the equivalent of what we call the total refractory time, which I'll explain in just a minute. So when the QT interval lengthens, it makes the relative refractory time longer, which can be potentially dangerous. And there's a lot of cardiac medications we give patients that can do this to a person. So it is something, it's a measurement that if I don't measure the PR interval, I may actually end up naming the rhythm wrong. if I don't measure the QRS interval, I may miss bundle branch blocks, which we'll talk about next week. QT interval, it's not gonna make a difference on what I name the rhythm. But if I see that the QT interval is lengthening, so I take care of a patient and their QT interval is 0.34, and then the next day it's 0.36, and now it's 0.40, I know something I'm giving them, some kind of medication we're giving them is causing this to happen. And the longer this becomes, the more potential danger there is for the patient. So interval measurements, again, PR interval, we start of the P wave to the start of the QRS. Normal, we said, is 0.12 to 0.20. QRS, beginning of that Q wave or whatever variation of the QRS we have to the end of the QRS. It's telling us how long it's taking the ventricles to depolarize. And the QT interval is the start of the QRS to the end of the T wave, how long it's taking the ventricles to depolarize, contract, and get back to rest so it can do it again. So refractory time is that QT interval. And what the refractory time is it's basically the QT interval. How long is it taking everything to depolarize, contract, and get back to rest? But within this refractory time, you have what we call an absolute refractory time and a relative refractory time. Absolute refractory time is from the beginning of the QRS to mid-T wave. So from the beginning of the QRS to mid-T, absolutely your heart cannot accept another impulse. Your heart is depolarizing here. It's trying to get back to rest, and not enough of the heart has gotten back to rest that it can accept another impulse. So the absolute refractory period, absolutely no way, no how is your heart going to accept another impulse. So even if something tried to fire early in that time frame, your heart cannot accept it. It's not ready to go again. But here's the problem, the relative refractory time from the downslope of the T down. By this point, a lot of the heart has repolarized. A lot of the heart is ready to go again, but not all of it. And so if you have an abnormal beat that fires on that end of that T wave, so you have this, something's causing electrical disturbance in your heart and something goes to fire on that downslope of the T wave, and your heart says, oh, I'm ready to go, and part of the heart says, oh, I'm not ready to go, it can actually cause electrical chaos for the person. It can actually put them in a lethal rhythm. And that's one of the reasons we say it is so important to measure that QT interval on a daily basis and see if it's lengthening. Because if this time span is lengthening, that relative refractory time is lengthening. And that means you're setting that patient up for the potential of having a potential lethal arrhythmia. So as I mentioned before, ECG paper is standardized. There's hash marks up on the top, and in between two hash marks is 3 seconds of time. So we can measure how many heartbeats I have in 3 seconds, 1, 2, 3, 4, and multiply that by 20, that would be 60 seconds, and then my heart rate would be 80 beats per minute. But generally, doing math in increments of 10 is a little easier, so most people will count heart rates between two sets of hash marks, which would be 6 seconds of time. Count how many beats, and then they only have to multiply by 10. The other thing you'll notice on our ECG paper is each one of these boxes, as I mentioned here, these dark boxes, is 0.2 seconds of time. And within that box, there's 5 little baby boxes, and each one of those baby boxes is 0.04 seconds of time. If we are measuring voltage, if we're going vertically and we're measuring voltage, each one of these little baby boxes would be 1 millimeter of voltage. So we are going to go ahead and take a break here, and then we'll do some practice strips of just measuring heart rates and intervals.